Imagine a lake at the very bottom of the ocean. Sounds like a glitch of nature? But what if I tell you, there is no oxygen there? The water kills in seconds, and yet life exists there. Today we will descend a mile deep under the Red Sea to see a black mirror that repels submersibles, preserves predators, and feeds entire colonies of creatures without a single ray of sunlight. What is this place? How did it appear? And why might the key to the origin of life on Earth and beyond be hiding right here? A mile beneath the surface of the Red Sea hides something that, by all the laws of nature, cannot exist. A phenomenon so strange that it flips our ideas about how life could have arisen on Earth, and perhaps not only on it. In 2020, the research vessel Ocean Explorer released a deep-sea vehicle into the abyss. 8 hours of combing the abyssal plain, and nothing. A desert with no signs of life, an eternal night, not a single stir. And then, when the crew had almost waved it off and was preparing to ascend, the submersible's headlights snatched from afar a murky silhouette spread out in a wide blot, about 20 meters across, as if a dark mirror lay on the seabed. They looked closer. Above the surface hung a dense haze. They approached and realized what they were seeing could not be. The surface of this giant mirror, not glass, not rock, not sand. It is water. How so? After all, they were already underwater. But right before their eyes, an underwater lake on the very bottom of the ocean, framed by a beach with barely noticeable slowed ripples, lazily licking the shore. Only a handful of people have had the chance to witness such a scene in person. And now we know one more detail that sends shivers down the spine. Any creature that dares to dive beneath the surface of this strange water does not return. And yet, here, in the dead darkness, there is something unthinkable, a primitive, alien form of life, existing not at all the way we are used to thinking about life on Earth. And now, fast forward to 2025. A sequence of astonishing discoveries has turned this surreal location into a key to rethinking how and where life can exist. For us, and possibly somewhere else. Where did this underwater lake come from? What can live there at all? And can the answer to this question hint at how it all began? Despite the giant leap in understanding underwater lakes in recent years, Ocean Explorer was not the discoverer. The first mention of such a lake dates to the 1st of March, 1964. A tiny note, a quarter of a page, got lost in a scientific journal. The author, the modest English oceanographer Henry Charnock, described anomalous water at a depth of 2 kilometers in the Red Sea. I can imagine what mixture of delight and quiet horror filled Henry's heart when calculations suggested at the bottom of the ocean an isolated lake might exist. What is it? From where? He did not know. He knew only one thing. It exists, and it defies intuition. Unwittingly, Charnock pointed at a mystery that would forever change our ideas about life on the planet. The clue he noticed looked like a trifle. The water was monstrously salty, far saltier than the water above it. This seemingly trifle is the first thread for us to pull as we figure out what these strange formations are. It seems incredible, right? How can there be a lake in the middle of the ocean at all? Do you know what the salt of the matter is here? Quite literally, in salt. The more salt is dissolved in water, the higher its density. That is why at the sea, you find it easier to float on your back than in an ordinary pool. Seawater is denser, and you, compared to it, become lighter and float. With the underwater lake, it is the same story. Ultra-salty water is denser than the surrounding water, so it settles in natural tubs and depressions on the seafloor. The density there is such that a submersible literally bounces off the surface as if from a trampoline. Purely theoretically, imagine you could somehow breathe and withstand the pressure. A hand lowered into this smoothness would feel a springy, viscous elasticity, like a giant water mattress. Scientists call such underwater lakes brine pools. They sometimes stretch for dozens of kilometers, taking the shape of lakes, rivers, and even underwater waterfalls. And the depth of individual bowls reaches hundreds of meters. A logical question: why does this brine not spread out and mix with ordinary seawater, forming a mush without a boundary? If you pour salt water into a glass of fresh, it will not settle as a perfect layer, but mix. What then holds the sharp shoreline on the very bottom? The answer lies in a tandem of two natural processes. The first bears a complicated name: double diffusive convection. And hello again to Henry. The anomalous water was not only very salty, but also unusually warm. Imagine a layer cake. Below, warm, salty brine. Right above it, colder and less salty seawater. Both salt and heat strive upward. Does that mean the top simply dissolves the bottom? In theory, yes. In practice, no, because heat escapes 100 times faster than salt. The upper layer above the lake quickly warms and rises higher, carried away by convection. And the very top layer of the brine itself, on the contrary, cools slightly and drops downward into the lake. As a result, the boundary film stabilizes. The sea above moves upward, the brine below downward. Thus, the knife-cut boundary line is drawn, that very hypnotic shore underwater. Do you notice the catch? Even with a sharp boundary, salt still seeps into the sea. Theoretically, the lake should melt like a tidal puddle in the heat, but it does not melt. The secret is that brine lakes are not puddles, but living systems in dynamic equilibrium. While the brine goes upward, molecule by molecule, from below it is replenished by a new flow. Warm, saturated, heated by the Earth's warmth and squeezed by rocks, this brine is forced upward to the ocean floor, drains into depressions, and behold, we have an underwater lake full size. The brine not only lies in wait for the unwary, it flows. In 2018, a no-way remotely operated vehicle in the Gulf of Mexico looked over a gentle ledge and saw a familiar scene: a dark blue bowl of brine around it, a cemetery of mussels, white shells like warning signs. But the camera rose higher, and something more spectacular than the bowl itself became visible. Long gray-black streaks across the beige slope. Tracing them, the researchers realized the brine was draining from above, down into the lake. In other words, before them was an underwater waterfall of brine. Its sources reach back to the Jurassic, 180 million years ago. Those very salt masses, as viscous as clay under pressure, are squeezed upward in pillars. Along them, the heavy brine, far denser than seawater, slides toward the lowlands and falls as a waterfall into the bowls. All right, we have figured out what it is and where it comes from. But who can live next to such a jacuzzi of death? The first impression is not for the faint-hearted. The shores are strewn with the bodies of fish, crabs, lobsters, and moray eels. Some have lain there for decades. The brine preserves them like a saline sarcophagus, turning the shoreline into an underwater cemetery of mummies. The death scenario repeats with frightening precision. A rare deep-sea fish swims up, more often skirting the bowl, and the moment it dips below the surface, within seconds convulsions set in. The fish writhes, the moray ties itself into a knot. It is a toxic shock from extreme salinity. The only salvation is to burst back out into familiar seawater. Alas, not all manage it. As if that were not enough, brine bowls are also anoxic. There is no oxygen here. Plus, a cocktail of toxic methane, Darkness, cold, crushing pressure, zero oxygen. The worst place on Earth for life, right? And yet, life exists. Colonies of bright green tube worms stretch like steps. Along the shores live giant, century-old mussels, shoulder to shoulder, entire mussel beaches. Between them, a carnival of creatures: shrimp, snails, comically squatty crayfish, and gelatinous crabs. Even large predators, fish, octopuses, fang-toothed morays, visit here to water, like at a savanna lake in Africa. But the main beneficiaries are slime-spawn hagfish, or many-gilled hypersurvivors, hagfish. These ancient living fossils, older than dinosaurs, hide right at the edge and wait until a victim is twisted by toxic shock, and at that moment drag the prey away. And here is what is strange. Only they seem insensitive to the action of the brine. They freely dive into the bowl and back out. Why is a riddle science is still unraveling. But even more surprising is not this, but what the entire world here rests upon. Spoiler, upon a poisonous gas. How can life be sustained where there is neither oxygen nor light nor photosynthesis? Until the discovery of such ecosystems, it was believed that all life on Earth feeds on the energy of the sun. Plants catch light and turn it into food. Then, along the chain, herbivores, predators, and so on, down to the deepest depths. Even in the abyss, where light does not reach, life depends on marine snow, crumbs of organics sinking from above, and its roots still remain the sun. But brine pools broke the script. These are oases completely independent of the star. Their energetics come from another source. Which? The hint hides inside the mussels that carpet the shores. Under the microscope, their innards are packed with bacteria. Not ordinary ones, but specialized. They can turn chemistry into food. Their favorite ingredient is methane. Fortunately for them, in the brine, there's a great deal of it. The process is called chemosynthesis. If plants eat light, then these bacteria eat methane, producing organic matter, the foundation of nutrition for the rest of the crowd. The irony of fate, what kills almost all large animals, is the very lifeblood of this ecosystem. The bacteria settle in the gills of mussels, a symbiosis of the purest water. The mussels give them housing and protection from filter feeders, and the bacteria provide nourishment to their hosts. In turn, the mussel quarters become shelters for shrimp, small crustaceans, and all the other brethren. An oasis amid the desert of the abyss impressed the first researchers. And somewhere here, many of them admit, there may be a window into the past to where life was only just learning to be life. Today, in 2025, one hears ever more often the thought, almost 4 billion years ago, life could have flared up in an environment very much like this. For a long time, the picture was different. In 1871, Charles Darwin, in an offhand letter, sketched the idea of a warm little pond with ammonia and phosphates. Yes, the very primordial soup in a shallow, warm basin with light and electricity in the form of lightning. The concept seized minds for 100 years ahead. But in the second half of the 20th century, when we found hydrothermal vents and other chemosynthetic worlds, the scenario broke. If life can exist without the sun, and the energy is a chemical soup from the depths, then why not begin there as well? For a long time, the favorites remained precisely the black smokers, tower chimneys that douse the seafloor with scorching, reagent-rich fluids. Around them, a riot of life, and all of it rests upon chemosynthetic bacteria. But now another candidate has stepped onto the stage: brine pools. As recently as yesterday, it seemed that such salty conditions were incompatible with life. Today, we see rich communities of bacteria and complex organisms, which means the survivability bar had to be shifted. And there is a detail that makes scientists rub their hands with excitement. The ancient oceans of Earth in the interval from 3.5 to 4 billion years ago were A. Poor in oxygen, B. Rich in methane, and C. Attention, very salty. What do we have that is poor in oxygen, rich in methane, and extremely salty? Correct? A brine pool. That is, the conditions in such bowls suspiciously resemble the recipe of the ancient ocean precisely at the time when life got started. No wonder many researchers consider them the best natural model of the cradle of life. And of course, the thought beckons further. If similar environments are possible on Earth, why should they not arise somewhere else? Two favorites: Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Under their icy crusts roar global oceans of liquid water. Judging by the data, they may be as salty as early Earth seas. That is, the set of conditions is very familiar. As recently as yesterday, such sub-ice oceans would have been written off as uninhabitable. They said, there is no light. Now, the story is entirely different. If life can feed on chemistry rather than light, then, in the black bottomless oceans beneath ice, there could also have appeared their own brine oases. Will we learn the truth? There is a chance. By 2030, NASA's Europa Clipper mission will reach Europa. The hunt for traces of life will begin. Yes, here begins the realm of conjecture. We still know too little about brine ecosystems to swear that life definitely began in such places, or that such bowls await us under alien ice. But one thing is indisputable. They have radically expanded the frame of thought about how the living can live, which means the deeper we dive into these surreal worlds, the higher the chance to find the incredible. Who knows what scatter of secrets already lies below the rim, waiting for our next expedition. We dive deeper. Remember double diffusive convection? Let us break it down without academic boredom. Heat goes upward 100 times faster than salt. It sounds like a dull figure, but visually, it is like this. Imagine two elevators. In the heat elevator, a high-speed mode, the doors bang, and it is already on the top floor. In the salt one, an old lift, barely crawling, cables creaking, passengers yawning. The upper ordinary marine layer manages to warm and slip higher before salt has time to seep there in serious amounts. And right at the rim of the lake, the upper film of brine, on the contrary, cools and sort of gets heavier. Therefore, it drops downward, replacing itself with a fresh portion of hot, salty solution from below. The boundary turns out not rigid but stable, like a skin on milk. Poke it with a finger, it trembles but does not fall apart. Now, salt tectonics in close-up. Ancient salt deposits behave at depth unexpectedly, not like a crumbly mineral, but almost like plasticine under a press. Layers of sediments above grow heavier with each passing age. The salt begins to creep, bulge, and work its way upward in diapirs, pillars, and domes. These salty candles deform the overlying rocks. The latter crack, and into the cracks, seawater extravagantly seeps. Below it is awaited by a salt supermarket. The water instantly becomes supersaturated with salt, is heated by geothermal warmth, and under rock pressure seeks an exit, where the bottom subsides. The result, a true hydro network at depth. Brine oozes, trickles, gathers into bowls like rain runnels in earthly gullies. Only the rain here is from the depths. A scene from an expedition. An ROV camera crests a ridge and ends up over a slope. Below, a dark bowl of brine along the shores, white bands of shells like safety stripes on a racetrack. But the main thing, the the streaks on the slope above. Long, bluish-black trails of sediment, like traces of spilled ink. Along them, the heavy brine, without mixing with seawater, drains into the bowl. We get an underwater waterfall. It sounds like an oxymoron, but the physics is simple. Dense brine is a liquid to which the ordinary ocean is cramped. Its path is downward to the lowest points of the relief. And if such a path runs along a fault or a hollow, we literally see a river and a waterfall, only all of it is underwater. Now, the unpleasant truth about toxic shock. The chief executioner is osmosis. Sudden contact with an ultra-salty environment means that water rushes out of animals' tissues. The cells sort of shrivel, like grapes thrown into salt. Neurons and muscles respond with convulsions. A fish writhes. A moray ties itself into a knot. Movements lose coordination. Add anoxia. There's no oxygen, nothing to breathe. And a cocktail of dissolved toxic gases, with methane as the star of the party. The result is predictable. If an organism does not instantly leap back into ordinary water, there is almost no way back. That is why so many mummies lie along the rim. The brine preserves them better than any museum solution. And now, a character who begs to be called the anti-hero of a documentary. The hagfish, our many-gilled slime eel. It seems to have signed a non-aggression pact with the brine. While others lose control, it patiently stands watch at the edge. And the moment it sees a victim go woozy, it slips inside, grabs, and drags away. Why can it do what is deadly to others? There are several working hypotheses. The unusual chemistry of the slime, for which these fellows are famous. Extreme resilience to changes in osmotic pressure. Special ions in the blood. Science frankly admits the final answer is still ahead. But it is already clear. The ecosystem here rests not only on bacteria, but also on such border janitors. Back to the feast's foundation, the bacteria. They live in the gills of giant mussels and do what to us sounds like magic. They harvest energy from the chemical bonds of methane, and sometimes hydrogen sulfide, to synthesize organic matter. This is chemosynthesis, an analog of photosynthesis. Only instead of photons, a chemical battery is plugged into the equation. It looks like a cooperative. The mussel provides housing and protection, the bacteria cook lunch, and the neighbors get crumbs and shelter. Thus, on the bare abyssal plain, a bubbling metropolis appears, independent of the sun and the whims of the surface. For a long time, the palm for the cradle of life belonged to hydrothermal vents, the black smokers. There, the energy is like from a fire hose, a hot chemical stream rich in reduced compounds, plus minerals that can act as catalysts for primary reactions. But brine pools have offered a weighty argument. They resemble the ancient ocean in three principal parameters: low oxygen, much methane, extreme salinity. That is, in such bowls, we see a living prototype of the chemistry that could have been the starting point. An honest bottom line? Most likely there were several cradles. Both smokers and brines could have played their parts. Nature favors not single solutions, but ranges. If we search for life beyond Earth, the checklist now looks different. We need water, even if under ice, sources of chemical energy, salts to tune density layers, and at least local pathways along which brine can migrate. Europa and Enceladus have in their favor global oceans beneath a crust. Is it dark there? So what? For chemosynthesis, light is not required. Is it cold there? Tidal heating works in the depths, which means chemistry proceeds. So yes, when we say brine oases under the ice, this is no longer fantasy, but a working hypothesis. And now guess, what will we do when we find at least a hint of such layered boundaries there? Correct. We will send everything that can drive, fly, and drill. And here's what is most important. Brine pools are not just another curiosity of the seas. They have expanded the very frame of the possible. They have shown that life is not tethered to the sun on a short leash, that it has backup batteries and secret passages, which means the more attentively we peer into this quivering border between sea and brine, the closer we approach our own starting point. Who knows what caches lie just a meter below the mirror-like surface, where the vehicle's headlights have not yet awakened the darkness? You know what? I am sure the most interesting finds are still ahead, and some of them may already be waiting right under our feet. Thank you very much for watching, friends. Write everything you think about this in the comments, and right now watch our previous incredible episodes.